Here are the solutions to your Chapter 11, Chapter 12 review problems. This will be Chapter 11, numbers 85, 88, 89, and 93, and Chapter 12, numbers 55 and 69. So I think a good coverage of types of things that you need to know coming up to our test. Alright, so what we got here, 85 from Chapter 11. Excuse me, I have a girl of mass m stands on the rim of a frictionless merry-go-round of radius r and rotational inertia I that is not moving. She throws a rock of mass m horizontally in a direction that's tangent to the outer edge of the merry-go-round. Speed of the rock relative to the ground is v, and then we want afterward what are the angular speed of the merry-go-round and the linear speed of the girl. So I've got the merry-go-round here. Here's the girl. And the merry-go-round has rotational inertia of I and a radius r. Girl has a mass m, and she throws a rock of mass m in this direction with a velocity of v. So the merry-go-round will sort of recoil, will rotate the other way. So this is a conservation of angular momentum problem. So before this would be kind of an explosion, right? It's not a collision exactly, but it's certainly a situation where momentum would be conserved, angular momentum. So before, nothing has any angular momentum. Nothing's rotating, nothing's moving. So before we have zero. Afterward, we have two things. We have the rotation this way of the merry-go-round, and then the angular momentum of the rock with respect to this point. And they're going in opposite directions, so one of them would be positive, one of them would be negative, however you want to deal with that. I'm going to make this negative. So let's see, the angular momentum of the wheel, the merry-go-round, afterwards. It's going to be I omega. The I of the merry-go-round is just I. But there's also a girl of mass big M standing on it at a radius of r squared from the center. So the wheel plus the girl, which we're treating as a particle, just an mr squared. So there's that. Plus the angular momentum of the rock with respect to this point here is rmv. And remember that when something's moving in its path from a particle, it's just that perpendicular distance that matters. So it's rmv. The sine theta I do not need. If I pick this point here, the r sine theta would just be this r. Right? And, oops, that's the I forgot the omega. Haha. Which is important because that's what I'm trying to solve for. So omega is going to be equal to rmv over I plus mr squared. And I think that's part A. And then in part B, they want the linear speed of the girl. Well, her speed of the girl is equal to omega times her distance from the center, which is r. She's at the edge. So it's just this times r. So that's equal to r squared mv over I plus mr squared. That's a good exercise in manipulating those relationships when you don't have any numbers. Number 88. A 1,200 kilogram airplane is flying in a straight line at 80 meters per second, 1.3 kilometers above the ground. What's the magnitude of its angular momentum with respect to a point on the ground directly under the path of the plane? So this is just one of these types of calculations. If this is the plane and it's going this way at 80 meters per second, point directly underneath. In fact, it doesn't matter where that point is on the ground. This answer would be the same because the r perpendicular is always going to be the altitude of the plane. I think it would have been a good follow-up to this here to say how does the angular momentum relative to that point change, and it does not change because the r sine theta will just keep giving you this altitude distance every time. Now let's see, 1.3 kilometers above the ground. What's the magnitude of its angular momentum with respect to a point? Okay, so that's all we need to do. This is a quick one. So r m v, and then sine theta in this case is 90 degrees. But as the plane moved to different locations, the sine theta would just, you'd have a different r, but multiplied by sine theta would just keep giving you this distance. And sometimes we write that like this. It's the perpendicular part of r. That perpendicular part of r stays the same all the time. So what do we have? 1,300 times 1,200 times 80. So about 1.25 times 10 to the 8th kilogram meters squared per second. That's units for angular momentum, right? All right, number 89. We have, with axle and spokes of negligible mass and a thin rim, a certain bicycle wheel has a radius of of 0.35 meters and a mass of, and it weighs, that's its mg, is equal to 37 newtons. So that means the mass is 3.78 kilograms. Now, what's all this stuff about the axle and spokes of negligible mass and a thin rim? So this is like a hoop, right? So they're telling us that so we can conclude. They're making a point of telling us that so we can say, oh, this is a hoop, so it's a full mr squared. So I'm going to go ahead and calculate that right now too, because I bet I'm going to need it. So I have m times r squared, that's 0.46 kilogram meters squared, be the rotational inertia of this hoop. It can turn on its axle with negligible friction. The man holds the wheel above his head with the vertical axle, with the axle vertical, while he stands on a turntable. It's free to. This sounds familiar. On a turntable, it's free to rotate without friction. The wheel rotates clockwise, as seen from above, with an angular speed of 57.7 radians per second, and the turntable is initially at rest. The rotational inertia of wheel plus man plus turntable around the common axis of rotation is 2.10 kilogram meters squared. So the I total is 2.10 kilogram meters squared when he's holding it right above his head. The man's free hand suddenly stops the rotation of the wheel relative to the turntable. So determine the resulting angular speed and direction of rotation of the system. And what is it going clockwise originally? Yeah, so if we're looking down at the guy's head, he's holding the wheel above his head, it's rotating clockwise, right? So the whole system, if we think about angular momentum, the angular momentum before and the angular momentum after must be the same, right? So before, the whole system is rotating at an angular velocity of 57.7. So I omega that's the initial angular momentum, and we want to find what is the angular speed and direction of the rotation of afterwards. So when he stops it, the angular momentum must remain the same, right? So, oh, whoops. Hold on a second. Before he stops the wheel here, he's not rotating, only the wheel is. So we need to use this, right? So the wheel's rotating, not him, just the wheel, at 57.7 radians per second. And then afterwards, when he grabs hold of it, then he's now sort of, basically what he's done is he's sort of coupled himself to the wheel so that they must rotate together. So now, whatever rotation there is, it's the total that is going to need to rotate, and that's what we're looking for there. So that's a simple calculation there. 0.46 times 57.7 divided by 2.1. So the final will be about 12.6 radians per second. And since the initial angular momentum was clockwise, this will also have to be clockwise. Right? Number 93. Have a body of radius r and mass m is rolling smoothly with speed v on a horizontal surface. It then rolls up a hill to a maximum height h. So I have something rolling along with mass m, radius r, speed v, and it encounters a ramp and rolls up to a height h. Right, that's its max height. If h is equal to 3v squared over 4g, what's the body's rotational inertia about the rotational axis, and what might the body be? All right, well, this looks like an energy kind of problem, right? So the energy at the start is a split between rotational and translational kinetic energy. It has both, right? It's rotating and it's moving. And then at the end here, I've got all gravitational potential. So let's write down the equation that shows conservation of energy here. So that would be our equation there. The rotational kinetic energy is 1/2 I omega squared plus 1/2 mv squared, and this is mgh. So I'll need to make some substitutions now. 1/2, I'm looking for the I, so I don't know what that is. I know that omega, since it's rolling without slipping, is v over r squared plus 1/2 mv squared is equal to mg times 3v squared over 4g. Alright, let's look for any simplifying we might be able to do here. That g here would cancel out, and I'm going to go ahead and multiply the whole equation through by 2, so I don't have any fractions there. So I have I times v squared over r squared plus mv squared is equal to, if I multiply this by 2, that will just turn into a 2 on the bottom, so that would be 3/2 mv squared. Right, so I can subtract this over to the other side, and I is equal to 3/2 mv squared minus mv squared is 1/2 mv squared, and then divide by v squared over r squared. and dividing by a fraction, same as multiplying by the reciprocal. The v squareds cancel out, and we get 1/2 mr squared, which is just the kind of answer we would hope to get for a rotational inertia. And then their follow-up question, part B, is, so what do you think that might be? And, well, that's the rotational inertia of a cylinder. So maybe it's a cylinder. Maybe it's not. Maybe it's something else that happens to have this rotational inertia. But it could be a cylinder, right? All right, that's the review problems from Chapter 11. Let's hit a couple problems from Chapter 12. Number 55. I have, let's see, in figure 12, all right, that's kind of a, maybe I'll copy this down. So I've got a block here, a knot here, an angle here, and another block hanging down like this. This is block A, this is block B. Shows uniform ramp. Whoops, nope, wrong problem, sorry. Block A of mass 10 kilograms and block B of mass 5 kilograms are in equilibrium. But it would slip if block B was any heavier, right? So this is maxed out. This is just barely hanging on by its static friction. For angle theta equals 30 degrees, what's the coefficient of static friction between block A and the surface below it? So this here, if this is in equilibrium, then the forces on this are balanced, the forces on this are balanced, but I think the important point, if you will, to look at is this point right here. The forces on this knot, it's connecting them, those forces are balanced. So this is the kind of static equilibrium problem. We do not need to use torque. Nothing's about to rotate here, right? So this is just a review of what we can do with static equilibrium problems. So here I've got 5G. It's not moving, so the tension is equal to that gravitational force, right? That's not true if it's accelerating. And then here I have, I'll call that T1, some other tension, T2. And here I have some other tension. Try to make that look more like 30 degrees. Call that T3. Right? Well, this is in static equilibrium, so that means the horizontal forces must be balanced, and the vertical forces must be balanced. So if the horizontal forces are balanced, let's see, if this is 30 degrees here, then this is 60 degrees. So I'm going to call this is like my cosine component of T3. So the horizontal forces, I have T2 must be equal to T3 cosine 60. That's this must be equal to that. And then 5G, which is T1, right, must be equal to this up part, and that's T3 times the sine of 60. That is where we are at. So I think we can chain through these equations and figure out first what T3 is. So T3 is 5G divided by the sine of 60. So that would have to be 56.6 newtons. And then T2, I don't even know if we needed to find that, but, oh yeah, I guess we did to get it here, didn't we? So then T3 is equal to that times the cosine of 60. Cosine of 60 is 1/2, so I'll just multiply that by 1/2. So T2 is equal to 28.3 newtons. Okay, now I'm going to make a force diagram for this block. So for block A. Block A, I have the gravitational force on it, the normal force on it, the T2 tension force on it, and the force of static friction. It's in equilibrium, so we're all equaled out here. And I know that the force of static friction must be equal to T2. And I also know this force of static friction, since it's maxed out, is equal to the coefficient of friction times the normal force. And so I think I'm good here, right? So the coefficient of static friction times 10g, because that's what the normal force has to be equal to, is equal to T2, 28.3. So the coefficient of static friction is 28.3 divided by 98, by 0.29. Cool, that's a good little problem. Could have done that problem back in chapter 5, 6? I guess 6 is when we did friction, so could have done that back then. No torque there. All right, I have a feeling there's going to be torque in this one. Number 69, we've got the wall with hinged rod kind of situation here. So here's the rod, here's theta 1, and then there's a rope here. Try to make that look more rope-like. We can tell the difference between the rope and the rod, because the rope couldn't be here and the rod couldn't be there. That wouldn't make sense, would it? Would collapse. And let's see, a uniform rod of mass m is hinged to a building at its lower end, while its upper end is held in place by a rope attached to the wall. If angle theta 1 is 60 degrees, what value must angle 2 have so that the tension in the rope is equal to mg over 2? All right, so let's see what we can do here. So we're looking for theta 2, right? And I don't know what this angle here is. This angle here would be, let's see, that's 180 minus these two, so that would be 120 minus theta 2. I think is that angle right there, right? All right, so let's see. I'm going to make my force diagram for this beam. Here's the beam. Take its axis to be here, so I don't have to worry about those, but I will put them in anyway because they're there. Here is the gravitational force, mg, acting at the center of mass, and here, acting at some angle that I don't know, is the tension force, but I do know that it's equal to mg over 2. And this angle here, let's see, I guess we could just, maybe I don't have to do that substitution. I could just say this is theta 3. Right? That's the angle I'm going to be able to work with though, right? Okay, so let's see. Taking the sum of all torques to be 0 about this axis, then I have two forces that are torquing this beam. There's this gravitational force and this tension force. So, and they are fighting against each other. So that must mean that F times R, they didn't say the length of it, did they? I don't think we need to know that. So it's at L over 2. Whatever the length is, I'm just going to call that L. Times the sine of the angle between them. So let's see what angle this is. These are parallel lines here, this one and this one. So if this is 60 degrees, these are alternate interior angles, so that's also 60 degrees. So that's sine of, sine of 60 there. And that must be equal to this other torque here, where I have, let's see, the magnitude of the force is mg over 2 times the full length, that's acting at the full length of the rod, times the sine of some angle theta 3 that I don't know yet. Well, looky what we have here. I've got mgl over 2, mgl over 2. Those cancel. Sine 60 is equal to sine theta 3, so then I guess theta 3 has to be 60, right? And if that's 60 and that's 60, then theta 2 is also 60 degrees. So that worked out awfully nice. We could have done that if, I think that would have been a better problem, in my opinion, if they had made the tension something else and we actually had to find some angle that was different. I think it would have been a little bit better problem if I had made it, but I didn't. There you go.